Welcome to the class. In this video, we'll learn the concept of continuity, its geometrical interpretations, and some important theorems on continuity. We'll also solve a few problems based on the properties of continuity. So let's get started. The intuitive idea of continuity is when we can draw a graph from a point x equal to a to a point x equal to b without lifting our pen. This graph connects the point A and point B without a break or cut or jump. So we can say fx is continuous in the interval x equal to a to x equal to b. Now let us write the definition of continuity formally. A function f will be continuous at x equal to c in the domain of f if limit x tends to c minus fx, that is the left limit at x equal to c, is equal to limit x tends to c plus fx, that is the right limit at that point, is equal to value of the function at that point equal to fc. If any of these limit or value is unequal or undefined, then the function will be discontinuous. In other words, limit of a function at x equal to c exists and the value of the function should be equal to the limit of the function at that point. Let us see some example. Now let us consider a piecewise function fx is equal to 1 if x is less than 0, fx equal to 2 if x is greater than 0. Here, the point 0, 1 and 0, 2 do not lie on any part of the graph. So obviously there is a gap in the graph when x is equal to 0. So this function is not continuous at x is equal to 0. In this case, left limit and the right limit of the function are different, hence the function is discontinuous. It is also clear from the graph. Now let us consider the second function fx equal to 1 by x square. Obviously, this function is not defined at x equal to 0. We can easily see that for this function, both left as well as right limit exist and are unbounded to positive infinity. Now if we zoom out, it appears that the graph is continuous. But if we zoom into the graph very far, we can see that both the parts of the graph never meet each other or the graph never cross the y-axis. Now, as the function is not defined at x equal to 0, it means that this function is not continuous at x equal to 0. So from these examples, it is clear that the function will be continuous at a point if its limit exists, means that left limit and the right limit at that point must be equal and the value of the function must also be equal to the limit at that point. Then only the function will be continuous. Now we will define a continuous function. A real function f is said to be continuous if it is continuous at every point in its domain. Now we will discuss two important theorems without rigorous proof. Theorem number 1. Suppose f and g be two real functions continuous at real number c, then first, f plus g is continuous at x equal to c. Second, f minus g is continuous at x equal to c. Third, f into g is continuous at x equal to c. Fourth, f divided by g is continuous at x equal to c provided gc is not equal to 0. This can be easily proved using the limits. Second theorem is, suppose f and g are real valued functions such that fog is defined at c if g is continuous at x equal to c and if f is continuous at gc, then fog is continuous at c. For example, we have to show the function fx is equal to sin x square is continuous. Let gx equal to sin x and hx is equal to x square be two functions. Now we know that sine is a continuous function. It is continuous everywhere in its domain, and x square, pi equal to x square, is also a continuous function. This is a parabola, so it is continuous everywhere. Both the functions are continuous. So g of hx, as hx is continuous everywhere in its domain, gx is also continuous because it's the sine function. So g of hx, that is sine of x square, should also be continuous function. That's it. So this much only in this video. In our next video, we'll solve some problem from the exercise. Thank you.